Now, we will give another basic definition that's very helpful for working with graphs, which is degree. So the degree of a vertex is the number of edges connecting to it. Very simple. And, or maybe more generally, in a directed graph, not more generally, but in this other setting, in a directed graph, remember that every edge has a direction, and so the endpoints are different depending on whether the edge is entering that vertex or leaving that vertex. So in a directed graph, each vertex has an in degree, which is the number of edges leading into that vertex, and an out degree, which is the number of edges leading out of that vertex. So for example, let's draw some graphs and label the degrees of each vertex. So here is a little graph, and we can just look at each vertex and look at the number of edges. That's the degree. So this guy has one edge leading out of it. So that has degree 1. This guy has 3 edges, which means it has degree 3, and so on. This has degree 2, this has degree 3, and this has degree 1. And if we add another edge out here, or another vertex rather, out here, with no edges, this has degree 0. And there are a couple special words for these kinds of things. A degree 0 vertex is called isolated. And a degree 1 vertex sometimes is called a pendant, because it looks like it is hanging off of the graph. And for example, so maybe let's even draw the same graph and give some directions to the edges. Now we can talk about the in degree and out degree of each vertex. So again, starting from over here, the in degree, well, there are no edges leading into this vertex, so that is 0. There is one edge leading out of this vertex, so the out degree is 1. And here, the in degree, so this edge is leading in, and no others. These two edges are both leading out, so the out degree is 2. And so on. This has in degree 1 and out degree 1. This guy has in degree 2 and out degree 0. And this guy has in degree 1. Oh, and of course, out 0. So that is the definition of the degree of a vertex. And there are some basic properties that the degrees of vertices must satisfy. So the first is called the handshaking theorem. Which is, for any graph, G, with its set of vertices and a set of edges, we have the following equation: sum of the degree of each vertex in the graph is equal to twice the number of edges in the graph. And there's a version for directed graphs, which maybe I will not write it down Or maybe I'll write it down and then erase it. So for directed graphs, the sum of the in degree is the number of edges, and the sum of the out degree is also equal to the number of edges. And you can prove that very similarly to how we're going to prove this. Well, let me start by saying maybe why it's called the handshaking theorem, because, of the analogy with a room full of people, and some of them shake hands with each other, and this is, how many people have shaken hands with other people, and how many handshakes occurred. Something like this. So the proof, this is quite simple. Each edge connects two vertices right? Because it has exactly two endpoints. And the degree of a vertex is the number of edges connecting to it. So if we think about what this sum is doing, we're going through each vertex in the graph and counting the number of edges that connects to it. And when we add those all together, we have counted each edge exactly twice. Because we counted it once for one endpoint and we counted it once for the other endpoint. And that's basically the proof, right? That tells you that the sum is equal to twice the number of edges because the sum counts each edge exactly twice. So this is some kind of restriction on, this is some kind of relation between the number of edges and the degrees of vertices. And here is one way that we can kind of give an interpretation of this restriction. So corollary, and I don't think I've used that word before, so if anyone's not familiar, a corollary is just another result that follows quite easily, or relatively easily, from something you just proved. So we just proved this handshaking theorem, and as a corollary, we can say that a graph must have an even number of edges of odd degree. Excuse me. And the reason for this is simply that, by the above theorem, the sum of the degrees of all vertices is even because it's 2 times the number of edges. And basically, it boils down to some basic facts about adding up even numbers and odd numbers. So maybe one way of saying it is that the sum of an odd number of odd numbers is odd. So for the sum of degrees to be even, there must be an even number of odd terms, which means exactly what we're looking for, must be an even number of vertices of odd degree. So let's illustrate these two facts we've just proved with a couple of examples. Maybe even the same example we were looking at before. So here's our little graph, and let's label again the vertices with their degrees. And we can just check directly for this particular example that the sum of the degrees is 1 plus 3 plus 2 plus 3 plus 1, which is 10, according to my notes. Adding up all those one-digit numbers is hard, you know? Which is 2 times 5. So how many edges are there? There are 5 edges. That checks out. And furthermore, how many vertices do we have of odd degree? Well, there's this one, this one, this one, and this one. So there are 4 of them, which is even. Again, that checks out with our theorem.